In this lecture, we want to learn how we can find the appropriate value for energy cutoff. The potential of a crystal is periodic because the crystal is assumed periodic. Thus, VR plus T equals VR. In this case, we can use Bloch theory. According to the theory, the wave function has two parts, UK and this exponential part. UK part has the same periodic of crystal potential. Thus, it can be expanded according to Fourier transformation. By substituting UK in this equation, we obtain the equation for wave function. We can see that psi is a superposition of plane wave with wave functions differ by g. G is the vector in the reciprocal lattice. This summation cannot be infinite, thus it should be truncated. This issue defines the cutoff energy. Indeed, G vector cannot go to infinite. Thus, cutoff energy determines the number of plane wave in the expansion to satisfy this equation. In the quantum espresso input file, we define the cutoff energy for wave function in this part with the unit of Rydberg. 1 Rydberg equals 13.6 electron volt. We have two types of energy cutoff, one for wave function E cut WFC and another for density E cut rho. By multiplying the wave function cutoff energy by a certain coefficient, the cutoff energy of density will be obtained. This coefficient depends on the pseudopotential type. For norm-conserving and PAW, this coefficient is 4. For ultrasoft pseudopotential, this coefficient should be between 8 and 12. Cutoff energy for wave function determines the size of plane wave. As the energy cutoff increases, the total energy decreases until convergence occurs. That energy will be its appropriate value. To find it, we should change the value of energy for wave function in input file to 10, 20, 40, 60, and 80. To do this, we create 5 different input files with different cutoff energy for wave function. For example, in this folder, this is input file, and the cutoff energy for wave function is 10. In this folder, this is input file, and the cutoff energy for wave function is 20. In this folder, the cutoff energy for wave function is 40. In this folder and in this input file, the energy cutoff for wave function is 60. And in this folder and in this input file, energy cutoff for wave function is 80. As you can see, we have 5 input files. For each input file, we run self-consistent field calculation and collect the total energy. We can find the total energy at the output file. For example, in this case, at the output file, as I said, in self-consistent field calculation, we find the total energy here. And for next input file, we can find the total energy here. And also for next input file, we can find the total energy in the output file. As I said, we have 5 input files. For each input file, we run self-consistent field calculation and collect the energy. We find the total energy at the output file. After that, we collect these data in a file such as ecut1. In this file, there are 2 columns. The first columns contain cutoff energy for wave function, and the second column contains total energy that is extracted from output file. By using GNU plot, we can plot this file. To do this, we open the terminal here and we write GNU plot. After that, we write plot, the name of the files that I created before, ecut1 with lines. You can see this figure. From the figure, we can find that the total energy reached convergence at the energy of AT. Thus, for the next calculation, we consider the 18 for cutoff energy for wave function.